Hello, everybody. So my name is Gabriel, and I'm here to tell you about our new approach to support interactive syntactic code search by giving semantics to in-progress queries using tree automata. Before that, let me give you some background. So if you've ever used a syntactic search tool, like the ones in the top right corner, you know that they actually search over trees instead of strings, which makes them, by also providing a query language that also gets parsed into a tree. Before doing some sort of tree matching to surface results. This actually makes them very accurate, being able to handle very complicated cases like the one shown here that has an infix expression and some commented out code. And the crux of it is that they just leverage a language specification. So they can handle things like white space, delimiters, nested expressions without any issues. And this also kind of implies that they're not actually limited to regular languages, like things like string search or regular expressions, which you may be familiar with, actually work. This makes them really cool, and I think that more people should use them. But it turns out that they don't really support this idea of in-progress queries. So let me give you an example. So going back to this same search, if we go one character back, right before you finish typing your search query, and you're just missing these last parentheses, the existing tools just don't parse. They just give you a parse error, and they give you absolutely no results, no feedback for you to continue authoring your query. And if you think about it, most of the states when you're typing a search query are actually not parsable, right? And so like the majority of these in-progress queries are just not supported. And I know what you might be thinking. Maybe we can come up with some error recovery or some new parsing technique to actually fix this problem. But it turns out to be a little bit trickier than that. And let me show you a different example. So imagine a developer is searching through the code on the right, and they want to find this example at the bottom, this method definition. So they start typing something like this. And this actually in the Semgrep, one of our baseline, will actually get parsed as an identifier and will only surface the top two results. If you keep typing, you may type something like this, which will now get parsed as a call expression, which will correctly filter out the first result, and it will focus on the second result. But notice that the intended snippet at the bottom is still not matched, because that's a method definition and not a call expression. If you keep typing, you might finally get to this, which again does parse, and it actually properly parses as a method definition, and it will actually surface the right result. But if we go back to the original search query, the problem here is that when the developer is typing, they maybe know where they're going, but whatever tool you're building will have a hard time trying to figure out what this ambiguous query might actually mean. And whatever parsing strategy you use, we'll have eventually to decide between parsing it as something like a call expression or something like a method definition, which are very different syntactic constructs with very different constraints. And so in practice, it seems like it's infeasible to actually use parsing to kind of like fix this problem. And this kind of impacts the interactive in-progress query support, because it means that as you provide extra refinements, your matches can actually change arbitrarily as it gets parsed in different things. Okay, so what do we actually want to build? The idea here is that what we want to support is this idea of providing results for all possible completions. Notice that this implicitly supports all unparsable queries, because all unparsable queries eventually can be completed as a valid query. But it also has this nice stable matching feature, where when we're searching for a query, as we refine our query by adding more tokens, we're just going to filter out existing queries, which means that at every point, we should be able to see all the results that will eventually match. And as we add more queries, we're just filtering out the ones that we don't care about. And so by doing this, we actually think we can actually support interactive in-progress queries. And for that, we implemented our tool, which I called ST-Search for sequence-to-tree matching, which I'll go into later. So now let me give you an overview of how the tool works. So traditional tools for syntactic search have an architecture that looks something like this. First, they do some amount of processing on the query, usually using the same language infrastructure that they use for the code, and they get a tree. And then they can use standard tree-to-tree matching techniques that have been around forever to actually surface matches. But as we talked about, this actually forbids us from supporting unparsable queries. So instead, what we're going to do is we're going to drop the parser and just use the lexer, which means that we're going to, instead of having a tree, we're going to have a sequence of tokens, but we're going to naturally be able to support most unparsable queries. However, this also means that we have to change our matching engine. And for that, we're going to introduce this new idea of sequence-to-tree matching to actually support these use cases. First, let me take a detour to talk more about what the query language is going to look like. So our query language is going to be just a sequence of query tokens. In particular, we're going to have a bunch of concrete tokens coming from the language that we're going to search over, but we're going to extend this with some wildcards to be able to express the patterns that existing tools are able to express. In particular, I'm going to talk about the subtree wildcard, but in the paper, I also developed this other idea for a sibling wildcard that you should go check out. Okay, so now let me give you an intuition about how these wildcards are actually work. So we already know that our query is going to be a sequence of tokens. You might have guessed by now that we want to match concrete tokens in our query to concrete tokens in our tree. But what about this wildcard? So I called it subtree wildcard, so that gives you an idea it should match a subtree. In this case, it should actually even match a token, since the token is considered a subtree. But notice here that it should match exactly just one subtree. So in this case, this is not a subtree. Like, even though there's a comma after our example, this would actually need to go over different tree boundaries, and we don't want to be able to support this since it doesn't seem intuitive. However, by leveraging this idea of matching a subtree, we can actually get arbitrary complex subtrees. And in many programming languages, a subtree often corresponds to statements or expressions, which means that we're going to kind of support these existing wildcards that exist in other existing tools. OK, so now we have to formalize this. So now I'm going to tell you about our technique for sequence to tree matching, or like the specific formalism that we came up with. First, some formalities. We're going to have a pattern, which is just going to be a sequence of tokens, and then we're going to have a tree. In particular, a tree is going to be a labeled ordered tree, which kind of corresponds with this idea of concrete syntax trees from parser. And our pattern is going to be a sequence of tokens. In particularly, this sequence should contain the labels for leaves in our tree, but extended also with wildcards, as we saw in the previous slide. And in particular, one of the things that is interesting here is that you can think of a pattern as specifying a set of trees, right? And this set of trees is a tree language. In particular, we suggest it's a regular tree language, similar to a regular formal language, which also means that we can encode this idea of matching a pattern, a tree matching a pattern, by actually specifying the automata that this pattern specifies, and then just saying that a tree matches this pattern if it's recognized by that automaton. I'll make a brief pause here to actually note that in order to actually support partial matches, we also have to support partial trees. But a slice of a tree is actually just a tree. So for the rest of this formalism, I'm just going to focus on matching an entire tree. OK, so now onto the tree automaton. So conceptually, a tree automata is just a top-down traversal of every branch of a tree. And we accept if it never gets stuck. And I'll go that a little bit more into detail once I give an example. But this is the entire automaton that we specify for this pattern, just for the subtree wildcard. So now let's actually walk through an example to see how these rules are actually working. First, note that the state at each tree is actually going to be the pattern that we're trying to match. So we start by specifying the full pattern at the root of the tree to say that we want to match this entire tree. And now we can actually use this first rule to actually propagate the state down by specifying which child of this tree are going to match which parts of the pattern. So we can propagate the state down in this way. And now we can see that our concrete tokens are all next to the concrete token that they're supposed to match. So we're going to have this extra rule to basically specify that whenever we have a concrete token in the pattern and a concrete token as a leaf of the tree, we can actually just accept at this point by dropping the state and completing the traversal. And so we can drop all of those concrete tokens. And finally, here is where we actually encode this idea of the wildcard by actually saying whenever we get a concrete, a subtree wildcard at any subtree, we can just accept since we implicitly match whatever the current subtree is. And so for that, we have this last rule, and we can actually drop the wildcard. And this shows that we've successfully matched this example, and it should give you an idea of how we were able to encode the semantics of our language using tree automaton. OK, so how about evaluating our tool? So in the paper, we have a bunch of different results, but I'm going to focus on the ones that we did to actually evaluate this idea of supporting in-progress interactive queries. So first of all, let's take a look at an example query. So if we have a query created by the following tokens, what we can actually do is just search all prefixes of this query and see how many results we get. And this is more or less what actually happens in our benchmark for this specific query. And you'll see here that as I mentioned earlier in the talk, as we add more tokens, what we want to do is filter out results. And we can see that that's the effect, the intended effect that we have. But now we can actually measure how much information, quote unquote, we're getting from each token by actually measuring how many results are getting filtered by each of these tokens. And so this is what that actually looks like. And now, one of the first things that you should notice here is that the first few concrete tokens are actually doing most of the filtering in terms of the search that you're doing. And in particular, you actually reach your final set of results halfway through this query, which means that we're actually, in theory, giving very good feedback. OK, now if we take a step back and you just focus on that last line, we can actually just graph that line for every query in our benchmark. And this is what the graph actually looks like. This is 161 queries that we extracted from a real-world benchmark that we've tokenized and graphed, running over roughly 100 NPM packages. And so you can see here that those insights from our previous slide kind of generalize, where a lot of the first few concrete tokens are actually doing most of the filtering, and you kind of saturate your final set of results often very quickly. So that's it for my talk. Hopefully you've learned that we can now support in-progress interactive queries for syntactic search. Thank you.
And we have plenty of time for questions. All right, while people are thinking,
great talk. Thank you so much. How do you handle multiple wildcards in the same pattern? Yeah.
Sorry. Yes. So this is actually handled by the transition system of the tree automata, right? So like different wildcards eventually end up getting propagated to different subtrees, and they have to be each of them have to be individually to be able to match. But it's kind of handled by the formalism and the algorithm that we also present in the paper.
Thank you for the talk. Great talk. Very minor question. What happens if someone's like in the middle of a word? Does it search for that partial token, or does it search for nothing?
So our current implementation assumes that you're given a full token or like a fully tokenizable query. So in this case, it'll actually parse that last token as a half a token, and it'll try to match it, and it might actually impact results. But this is actually not really a limitation of our work, because really you can insert like a token that's supposed to be like where the cursor is, and just say that the previous token and that token should match like the prefix instead of the complete token. So like this is something that we didn't test in our implementation, but it should be fairly forward to extend. Yeah.
Thank you.
Hi, thank you very much for the talk. I wanted to ask if you're inspired by, or have you considered applying methods from how IDEs could do syntax highlighting for partial code? Maybe they could also be applied to this domain.
Yeah, so we were not inspired by it, but we realized as we were working on this project that this idea of just relying on the lexing of the code instead of the parsing is actually what traditional syntax highlighters do. More modern syntax highlighter actually will parse the code and try to do semantic parsing, it's called, which means that it kind of goes a step forward. But there's no reason that we cannot integrate this approach with also approaches that actually parse the query if it's actually parsable and try to give better results in that case. This is just like to support the cases where we cannot do that.
And thank you. As follow-up, I know that some languages have context-dependent keywords that can serve as different types of tokens depending on the context. Are you able to handle such cases?
Yeah, actually JavaScript, which is one of their languages, does have that. And one of the things that we do in our implementation or in our formalism is we just take the token to be the text of the token and not the type of the token. In theory, if you have a language where keywords are always keywords, for example, you could like make that stricter and make it match the type of the token. But in this case, we don't actually care as long as it's guaranteed that the token gets lexed correctly.
OK, thank you.
Yeah.
I was curious about the particular kind of tree automata that you chose. There's a lot of different kinds, and these are top-down versus bottom-up. Is that right?
It's top-down, non-deterministic finite tree automata.
And is there any implications by using top-down? I think they're slightly more restrictive than bottom-up, as I recall.
So non-deterministic top-down automata are not more restrictive. They're equivalent to bottom-up automata. It is true that you cannot implement this as a deterministic top-down automata because it is not path-dependent, which is the specific property. But you actually don't want to implement this as a tree automata because the split pattern rule here over here actually has a combinatorial explosion and all the possible choices that you can make. In the paper, we actually give an algorithm that's deterministic and uses backtracking to actually do that in performance that seems to be fine, but there's potential for improvement there as well.
So is part of the issue with using the bottom-up that you start with the tree wildcards at the leaves and can match a lot of possible things? Is that the issue?
Yeah. So I mean, I was thinking about it as top-down non-deterministic automata, but I think actually bottom-up would, in theory, give you better performance because you're kind of just constructing all the sub matches and then trying to unify them. We didn't empirically check this, so all of this is just based on intuition. Yeah. Thank you.
I guess I have one more question. So I think this kind of incremental matching is useful when it's extremely fast, because as you're typing, you want to see the results. Do you have results of the performance of the matcher actually?
Yes, we have them in the paper. I'll briefly put them in the screen. In practice for a single project, it's extremely performant. It's about as fast as parsing the project. We do think that if you're working on a large-scale code base, or if you're searching over the entire internet, then performance might be a problem. But really, existing tools have years of tree matching experience, with indexing and other optimizations that they can leverage. So we think this is the first step in actually introducing all of those optimizations to this semantics.
All right, awesome. All right, if there are no more questions, then let's thank Gabriel again.